Hello everyone. We're going to go over AP free response problem given in 2004, the fifth question. It says that the graph of the function f shown above consists of a semicircle and three line segments. Let g be the function given by g of x equals the definite integral from -3 to x of f of t dt. So note that g accumulates area under the graph of f on the interval from -3, it always begins at -3 to some number x in the domain. Okay, now as soon as we see this, that a function is defined as the definite integral of -3 to x of f of t dt, before we read on, we should immediately realize that the derivative of this function is f with x replaced for the t. Okay, this is the Fundamental Theorem of Calculus Part 2. And when the readers grade this question, they look for this somewhere on your paper. This is a very important statement. So that's the first thing we should write whenever a function is defined in terms of a definite integral, where the upper limit of integration is just x. Okay, now we could start. So part A asks, what's g of 0? Well, g of 0 is -3 to 0, the definite integral from -3 to 0 of f of t dt. So we look at our graph and we look at -3, which is from here, to 0. So this is asking for the area of this trapezoid, which is above the x-axis, so it will be positive. So let's see. Now, the bases are the parallel sides, and the height would be this segment here. And the height, we could see, is already 3. The bases are 2 and 1. So using the trapezoid formula, this integral equals 1/2 the height times the sum of the bases, which are 2 and 1, and the answer is 9/2. And that is the answer to that definite integral, which is g of 0. So remember, the domain of g are the x values in the domain of f, and whatever is replaced for x goes up here in the limit of integration. Now the next question says find the derivative of g at 0. So because we have this equation, that's the general derivative formula, the derivative of g at 0 is f at 0. And if we look on the graph, we look at what the value of f is at 0, and that is 1. So that answers that question. So let's put a little circle around it. And that completes part A. Okay. Now part B asks, find all values of x in the open interval from -5 to 4 at which g attains a relative maximum. Justify your answer. So going back to the fall, g has a relative maximum. Well, we have to find out when the derivative of g is 0. These are the candidates, right? And this is the same as saying when f of x equals 0. And we see that f of x equals 0 and this is where the graph of f crosses the x-axis, and that would be at -4, 1, and 3, looking at these points, -4, 1, and 3. So we make a number line using the same domain as f, which is -5 to 4. we put in these critical values, -4, 1, and 3, and we label on number line the derivative of g, which is really f. So the graph of the derivative of g is the graph of f. So this gives us two things. And when we want to see when that derivative is positive or negative, we look at the graph of the derivative of g when it's above or below the x-axis. So from -5 to negative 4, the graph of the derivative of g is below the x-axis. From -4 all the way to 1, above the x-axis. From 1 to 3, above the x-axis, and from 3 to 4, below. So when the derivative of g is negative, the graph of g is decreasing. And when the derivative of g is positive, the graph of g is increasing. So looking at the increasing, decreasing behavior of g, we could tell where their relative maximum and relative minimum. But this asks for relative maximum. So we'll say that g has a relative maximum at, well, let's think about it. Well, from -5 to -4, the graph of g goes down and then up, keeps going up and then goes down. So it looks like the maximum would, a relative maximum would be at 3, because the derivative of g, which is f, changes from positive to negative. And that's all we need to answer the question. If they asked for relative minimum, g has a relative minimum here at x equals -4, but they didn't ask that, so we'll just leave it. So let's just put a box around our answer there. I lost the page for a minute there. Okay, and that's our answer. Now, the next question asks for the absolute minimum value on this interval from -5 to 4. So again, these are still our critical values, -4, 1, and 3. But since we did a number line analysis of the sign of the derivative of g, we know that -4, g has a relative minimum at x equals -4. G has a relative maximum at x equals -4. And since, I'm sorry, at x equals 3, I meant to say 3 there. Let me just erase that. At x equals 3. And only because we went through the number line analysis, we don't need to test 3, because there's a relative max, so there can't be a minimum there. And in the same way, we don't need to test 1, because the graph of g keeps increasing, so there's nothing happening at 1. So the only points that we need to test for the closed interval test are the endpoints, x equals -5, x equals 4. We don't need to test 1 because we looked at the sign of the derivative of g. Nothing's happening at 1. We don't need to test 3 because we know that g has a relative max there. So the only other point we need to test is -4. If we did not have this number line analysis here, then we would have to test 1 and 3 as well, if we didn't realize that there was a relative max for g at 3. So these are the only ones we really need to test, using the closed interval test because it's the absolute minimum value. So let's do that on the next page. Oops. So we set up the closed interval test by putting the endpoints of the interval and all the points at which the derivative of g equals 0. But of course, we eliminated 1 and 3 because we've investigated that. So what we do is we substitute it directly into the definition of g. And let's see what we get. The first one would be the definite integral from -3 to -5 of f of t dt. The next one would be the definite integral from -3 to -4 of f of t dt. And the last one would be the definite integral from -3 to 4 of f of t dt. All right. Now let's see if we could evaluate these. Now, when we have a definite integral, it's understood that when we say the definite integral from a to b of f of t dt, preferably we want the lower limit of integration to be smaller than the upper limit of integration because we always accumulate area from left to right. So in the first integral here, we will flip the limits of integration since -5 is smaller than -3. But when we flip the limit of integrations, we negate the answer. And the same is true for the next one. Negate the definite integral from -4 to -3 of f of t dt. So remember, -5 is smaller than -3 and -4 is smaller than -3. These numbers are further to the left on the number line. But the last one's okay. I mean, that's fine. Now, to find the answers to the definite integral, we find the total net area under f from left to right. So we start with the first one, the definite integral from -5 to -3. So I'm going to underline this in red. So you see that from -5 to -3, we've got these two triangles. One triangle is below the x-axis, the other one is above the x-axis. But notice that both of these triangles have the same length measure as a base and the same height. So this has an area of -1 since it's below the x-axis. This one has an area of +1. And when we add them, the answer is 0. And just looking at the symmetry, you could see that the answer is 0. So try to use symmetry as much as possible to see where the sum would be 0. If this area below the x-axis is identical to the area above. All right, now for the next one, but we negate the 0. I should say, technically we negate the 0, but that's still 0. So that doesn't matter. Now, from -4 to -3, let's look at that. All right, that's from here to here. We know the answer is just +1, but don't forget to negate it. So we have -1. And the answer is negative only because the original area was positive, but we're negating the answer. And then now I'm going to do this one in green. From -3 to 4, so we're looking from here all the way to here. We have to find this total area. Okay, so I'm going to split it up into parts that we could recognize. All right, now let's take a look at the trapezoid. The trapezoid here has a base of 3. Okay, well, actually, the height is 3. One base is 2 and the other base is 1. So to get the area of this trapezoid, we have 1/2 the height times the sum of the bases, which are 2 plus 1, and that would give us 9/2. Okay, so we put 9/2 here. All right, now to get the area under the semicircle, notice that it's a little different from the other problems. If the semicircle was here, then we would take its area. But actually, it's the area under the semicircle. And to get that, we have to get the area of that rectangle and subtract the area of the semicircle. So the area of the rectangle would be 2 times 1, which is 2. The area of the semicircle would be pi times its radius, and its radius looks like it's 1 unit, times a half, pi r squared times a half, which is pi over 2. So the area of the region in green below that semicircle would be 2 minus pi over 2. Area of the rectangle minus area of the semi would give you the area under the semicircle, because the semicircle itself is not included into the area. So we subtract. So we have to subtract 2 minus pi over 2. And then we have these last two triangles here. But notice that these triangles are symmetric. One has positive area, one has negative area. So the sum of these two areas would be 0. So we add a 0. So the final answer there, if we combine like terms, would be, okay, let me just put a little cloud around this because it's separated, would be 9 over 2 minus 4 over 2, 9 over 2 minus 4 over 2 plus pi over 2. I think that's right. Oh, we're subtracting here. I mean adding, I'm sorry, because we're adding the areas. So this is addition. So this would be 13 plus minus, I got my signs mixed up here. All right, let me just erase this. This is minus, so it's 13 minus pi over 2. We need to combine to tell where our absolute minimum is. So let's look at it. Pi is about 3 point something, so this is certainly positive. 0, well, that's neither positive or negative, but -1 is the smallest value we have here. So the answer to the question is that, okay, let's just put the answer here. The absolute maximum, the absolute minimum value, okay, so we have to write down the value, is -1. Is -1. And this is our justification. This would be accepted as a justification, showing the reader that you have to substitute the endpoints and the critical values into the original function. And then the last problem asks us about finding all values of x in the open interval -5, 4, at which the graph G has a point of inflection. So let's look at it on the next page. So remember, this is the graph of the derivative of G. This is important. This is the graph of the derivative of G. And if we're given the graph of any derivative, we could find G's inflection points. So let's write this down to review because it's very important. Okay, we could find the inflection points when the derivative graph increases, G is concave up. When the derivative graph of G decreases, G is concave down. So to find inflection points, the derivative graph of G has to change from increasing to decreasing or decreasing to increasing. So we trace the graph of the derivative of G from left to right. So let's do that. So we start from the left. So the derivative graph here is increasing. And then the derivative graph here is decreasing and keeps decreasing. Then the derivative graph increases a little bit and then decreases. So it goes up, down, down, up, down. So the x value at which the derivative graph of g changes from increasing to decreasing must be the inflection points. So our answers are g has points of inflection at x equals -3, at x equals 1, and at x, and I think that's, and at x equals 2. These are the 3 points of inflection. It didn't say to justify, so this is enough. It could be answered in one line. But if they did say to justify, we would say because the graph of the derivative of g changes from increasing to decreasing or from decreasing to increasing. But that's only if they asked us. All right, that takes care of this AP. I hope you found this helpful, a helpful review, actually. Okay, take care now.